ever get any better goal node, and you're just not going to ever expand this. Do you understand what I'm saying? So at this point, let's say this was 9 and this was 9, okay? And so because you're breaking ties arbitrarily, you could be picking this. And then you expand this, you get a 0 extension, still 9, you pick that, expand it, another 0 extension, you pick that. You keep on doing this, you never actually consider this guy, because of which you don't complete. So you need one more condition. Not only should the edges be non-negative, they should actually be non-zero. So the requirement for uniform cost search to be optimal turns out to be that it's complete, it's optimal. Okay, yeah. If the edge costs are positive, then essentially you are guaranteed that you would terminate as well as will be optimal. That's uniform cost search. Okay. The other question is, one of the things that I think that gentleman was asking earlier, what if, in fact, a variation of that, what if there are multiple paths between nodes? In particular, what if you wind up having undirected edges so that you can go back and forth and back and forth and back and forth between nodes? In fact, if you have just two nodes with zero cost edge transitions between them, that's good enough. You just keep going back and forth between them. But since I'm not allowing zero cost, it's at least the epsilon cost. When I keep going back and forth, I will continually increase the path cost. Eventually, the path cost becomes larger than the optimal path cost. So then I will pick the optimal when I start. Okay, so that's basically the reason why the optimality of uniform cost search is not affected by there being cycles. It will still work even if there are cycles. The only requirement is that the edge costs are epsilon positive. Okay. One last thing I want to do, and then we'll take a break, and so basically you can come back and talk about A-star search, is it looks like everything is nice in uniform cost search, but consider this graph. Everything is fine, everything is positive, all edge costs are positive, right? Okay. What happens on this graph? Does uniform cost search find the optimal solution? It better, because I just said I proved that it will find all this, right? It will. The real question is, will it do well on this graph? No. Why? This is what I call bait and switch graph, right? It's basically when you are here, A and B, so node B is only 0.1, node G is 9, we say, wow, B is only 0.1, let me do that. Then I get to C, it's only 0.2, this is 9, so let me do C. Then D is only 0.3, G is still 9, so let me do D. Now the interesting thing is, between D and G, I can put another humongous number of nodes. And for each of those nodes, furthermore, I can put big subtrees under them. So much so that uniform cost search will spend a whole bunch of time looking at all those useless nodes before picking G. Do you understand what I'm saying? Whereas it should have picked G up front somehow. Then it would have been much nicer. What happened here was the costs were misleading it. And so because the costs were misleading, it's only looking at, this is the problem of being only aware of how far you have come, not about how far you have to go. There are two parts to search. One is how far have you come, the other is how far do you have to go. Uniform cost search basically assumes that it doesn't care about how far it has to go. Okay? And because of which, it essentially really assumes that B looks better than G, C looks better than G, D looks better than G, and many other nodes which all have this 0.1 transitions will still keep looking better than G. But if you do the reasoning of how far do you have to go, from G, how far do you have to go to the goal node? 0. It's a goal node. If you have some kind of an idea as to how far you still have to go from C, if you have just some idea, and if you added that to how far you have traveled, and then compared those apples to those other apples, then you are in a much better shape. So right now, what you are doing, the reason you are failing is basically on that particular graph, you're failing because you are continuing to compare G of n and G of n dash. But really you want to compare G of n, which is the cost incurred, and you also want to compare H star of n, which is cost to go. Cost to go. How much cost you still have to incur to reach the goal? If I give you H star of n, and then I can then compare, so I can compare this sum to this sum, I will assume that G plus H, I will call this to be F. If I compare F of n and F of n dash, and if I do the Q's in terms of the F values, then I can do much better. In particular, if I have H star is the exact cost to go. What is the optimal cost to go left to the goal state? Okay, let's actually look at this graph and say, what's the optimal cost to go for A? 9. For B? What is the optimal cost to go from B to G? No. Okay, who said 0.1? Okay. Anybody else has any other answers? To go from B to G, you're looking at the entire graph. Your search algorithm doesn't, but you're looking at the entire graph, so you should be able to answer this. What? 25.2. You saw the entire graph, right? It's like basically from B you have to go to G, 0.1 plus 0.1 plus 25, 25.2. Do you now see it?
No, I see it, but I thought we're taking notes from note. We're not looking at it.
No, so this is cost to go. I am asking for something that's hard to get. Okay? H star if you basically the next thing that we would say, if I do have H star, for every node, and if I do uniform cost search on it, using, I do the first in, first out, I do the priority in terms of F values. That would be the optimal possible search in terms of efficiency. It would only ever expand nodes that fall on the optimal path. It will not expand anything else. Do you understand what I'm saying? So, in the break, if you can figure out how to get H star, we are done. And in fact, one of the things you can do is run another search algorithm on the side, which computes the H star, and it supplies it to your other algorithm. And that way you can have this Pyrrhic victory saying, look, I done well. Because getting H star, optimal H star, involves solving the problem. It's a stupid idea. But as stupid ideas go, it's a good stupid idea because it tells you how to improve. H star is hard to get. H star is hard to get because it's the exact cost to go from this node to the goal node. And the only way you can do it is to actually do another search. But what if I don't care about H star, I only care about H hat n, which is, I'll just call it H of n, which is an approximation to H star. I just want an approximation to H star. Approximation should be easy to get. The real question would be, what side do you want? H star is a real number. Okay, when you're approximating H star, you're going to either approximate it by under bounding it or over bounding it. Which approximation is good? I will argue that if you start thinking this way, uniform cost search is already using an H of n. Normal uniform cost search is using an H of n. Equal to 0. That's what it did. G of n, you just thought it was using G. but it's actually using g of n plus h of n, where h of n is always 0. That's why it was doing search with just g of n. Now, h of n being 0 is going to be lower than real cost to go, because we did admit that all our edges will be positive cost edges. So you already know which side is the better side in terms of optimality. As long as the approximation of cost to go is optimistic, that means you think they have less cost to go than it actually is the case, you are guaranteed to find the optimal solution if you were to do search with g plus h, where h is a lower bound on h star. Okay? If on the other hand h is not a lower bound on h star, if it is an upper bound on h star, then let's look at the other extreme. Imagine h of n is set to infinity. For every node you think the cost to go from this node is infinitely far. What would you do then? It looks like life is not worth living. Right? Because this node, I've come 9 units long and I have infinite more units to go. This one I have 10 units long and that's another infinite more units to go. To heck with the search problem, I go die. Right? Basically, all the nodes are equally bad and you can guarantee that there is no solution. So in that case, the search efficiency is extremely high because you get done very fast. Suicide is very efficient. It's not particularly optimal. Because after your suicide, you would realize that the exam has been shifted by a day. And it's too late. Do you understand what I'm saying? Okay? So, if you overestimate the cost, you are no longer guaranteed optimality. If you underestimate the cost, you are guaranteed optimality. If you underestimate it too much, you are just as bad as a blind search. Overly optimistic people thinking exams will be always, postponed won't do too well. Overly pessimistic people thinking that Rao is actually going to ask me questions about Chinese in today's class would probably didn't show up to the class and are missing this great lecture. Okay? The reality is you should be just below H star and as close to H star as possible. Come back from your break of 10 minutes and we'll talk about the fact that in fact we can prove that this will be optimal and then talk about how to get such things.